Welcome to the course on FPGA based signal processing systems, as we are doing the synthesis of combinational and sequential logic circuits. Here is the few more examples of the sequential logic circuits which we had already coded and with the Verilog module, and the Mealy and Moore state machines. One examples of that I had taken and show you that synthesis of these state machines, especially the Mealy state machine, which has the input also along with the current state decides the output logic, whereas in the Moore we have this current state decides the output logic. So we will see this synthesis diagram of the RTL schematic under the technology schematic, in which you can see the input merely state machine input, which also connects to the output logic, what we have coded in the Verilog module also. After this, we'll be doing the sequence detector as well. So one synthesis on sequence detector, so that the three examples would give us the details about the implicit and explicit state machines. So the implicit one, which we had seen in the previous lecture, that has it doesn't make continuous or the explicit state transitions. Instead of that, it makes the storage of flip-flops, realizing as flip-flops, it makes the storage and the ripple counters, and the one example we took. Now we'll see the explicit state machine examples in this synthesis process. So Mealy state machine, the example which we took already, and this is also the Verilog modules are developed for this state machine. Mealy one in style 1, 2, 3, 4, 5. If you remember, that style 1 I had taken for this example here to demonstrate that how the synthesis process look like after this coding. So then from the diagram, which is we have the next state logic, in which the states, the current states are A, B, C, D, and enable is 0, that moves to next state like this, and giving the outputs also 0, 0, 0, 0, and when enable is 1, that the next states are listed here, the outputs are shown over here, except at D, moving from D to A, the output is 1, remaining states it is going to be the output is 0. So this is the state transition table, and it also shows the output along with that, which state it is moving and the output. So from the Mealy representation, I believe this is now understood, that input slash output, and it's when the input is 1 and the state moves from A to B and giving the output 0. So similarly, it can be interpreted in other states as well. So now coming to the module, we have taken the clock and the enable. Anyway, clock is used to move from one state to another. At passage of the clock, if you remember, that SREG is assigned the S next value. So enable is that input we mean here, the clock enable. Output is the current output. This is current state, and this is next state, and the output Z. So SREG and S next are 2 bits here. If we are declaring it the SREG, SZ, and reg S next, and then define the states using the parameter construct. So one, that is 0, 0, 1, that's 2 bits of A bit. A is 0, 0, 0, 1, and C 1, 0, D 1, 1. So these are assigned 2-bit states, as we have seen this already. So and now the state memory. So the example here is it is a style 1 code. So we have the 3 different always blocks for each one. The combinational logic, each combinational logic, like next state logic and the output logic, we have the 2 always blocks separately, and for state memory separately. Always at passage of the clock, this S next is assigned this. So this is explicitly saying that in this state machine, that assign this X next to XREG. And in the next state logic, because the Mealy machine takes the this also in case SREG, and if it is from the table we have just given this, if enable equal to 0, then stay over, move enable is 1, move to B. If it current state is B, then this is if enable is 0, and this is what is written in the if with the if else statements. So let's see this if else statements, how default state is next equal to a. Okay, so the in case and n. This one, let us see this how this always block is getting realized in the synthesis process. Also the always at passage of the clock is next is this is again. So here clearly this should identify the edge sensitive behavior. If we use reset, if we have multiple edge sensitive behavior, then which one should be clock? There will be a dilemma that which is clock. So if we have the only one edge sensitive behavior, yes, it's obviously this is the clock over here. We have not used reset in this. I'll show you the example with reset as well. So it is better to have the reset to have more control over the state movement. Wherever the state is the state of the machine, state machine is there, then we can bring it to the initial state or then by using the reset. So this is the two always blocks, and the output logic is also coded with another always block, which you can see enable or sreg, and if this is 0, here all the cases this is also put in the enable condition if else statement, remaining 4 of them in case your default is at 0. So this would also be this if else statement, how it is going to be synthesized. So the case statement, which has all the, it has the default case as well as the if statement has all the else conditions. So there won't be any problem of combination logic synthesized into a latch. Okay, so here it should be a mux structure, and similarly the previous structure, always block also, the next state logic also should be realized as a mux structure. So from this, the RTL schematic, if you look at the RTL schematic, yes, this is the clock, the passage of the clock here, the making transitions, or the next state is assigned to sreg, the current state. So you can see the 2-bit sreg, which is over here, the 4 states A, B, C, D possible ones, and enable is the input, and which helps to depends on the enable states or moving from one to another. You can see over the this mux, which is the output logic, simply as 0 0 0 1 1 0 1 1. These are the four cases here it is mentioning. The select bit is here 0 because of the 4 input, the 4 input mark, 4 to 1 mux, which is giving Z here. So it checks for the enable also. So and the current state is given to the select bit. So why this is 2-bit is that the current state is given to the select bit, and the enable also is coming as an input to the mux. Okay, so this is what the Mealy machine takes the input in the output logic, and rest of them, the 4 mux, which is deciding the next state logic, that is if else statements, if enable is 0, and then move from one state or stay over there or move to another state. So these muxes are taking only yes, enable is 0, enable 0 or 1. This is 1-bit enable, you can see over here, and the other here to decide the next state. So this is giving the next state, and that next state is assigned to sreg to the D to have the current state here. So this is the logic. This mux takes the inputs from these small muxes, that is 2 to 1 mux, to decide the next state logic. So the next state logic coming to the sreg. So we have x next, and this is sreg, the outputs of 2 bits, and the state machine output. So this is RTL schematic, which is having no problem here to have the synthesis process. It is having the mux structure, the if else statements are clear, and in the case structure even we have the default statements. And this is related to the state memory, output logic, and the next state logic. This whole thing covers into the next state logic. So coming to the technology schematic, so the clock, it is used with the LUTs. Of course, this mux function is realized in the LUTs, using LUTs. So the SREG and a 0 and 1 bit, that is 2 bits having the flip-flops. Flip-flop for each state, it has to A, B, C, D, it has to move. So the 2-bit SREG which is coming from the output of the 1 and 2 can be seen. Also SNext, which is going to this, you can have this SNext, it's also going to the D of this as well as D of here. So 0 and 1 bit, which is giving the outputs as SREG. So as we have seen in the RTL schematic also. So the LUTs, so deciding this SNext instance, 2 input and 3 input LUTs are sufficient to decide the next state logic. Here this is the 2 input and 3 input LUTs from the if-else statements, and the output logic which uses the 3 input LUT. You can see that the Q over here and this over here. So that means SREG is given over here, and the enable input which is taking into the LUT as a third input. So this is the output logic. So the technology schematic also shows this flip-flops and the output logic which takes the enable also as an input, okay, and the next state logic is decided by this LUTs over here. So SREG, SNext, and the output logic in the technology schematic, the synthesized version of the Mealy state machine, that style 1 we had. So the LUTs function, Boolean functions are obtained over here, that is LUT 2 input and the 3 input and 1 for the output. So this is 2 for the next state logic, and this is 3 input LUT, which is the optimized function over here, Boolean function obtained from the synthesis process. So that Mealy state machine. So we'll take one more example of the Moore state machine, which has been used in the design. Also we have coded this we developed this module, Verilog module of the Moore state machine, in which you have these 2 flip-flops and combinational logics. So the output here, this is the output logic, and these 2 gates form the next state logic. So for the D input and this another D input. So the corresponding equations we had obtained, if you just go back and refer the lecture of this Moore state machine, we have explained this D0 and D1, how we obtained, and Z also the corresponding excitation equations, and the output equations are those. And from that, this Q0 star and Q0 star, the next state logic because of the D flip-flop. So from this we obtain the state diagram, this Q0, Q1, enable 0 and enable 1, in which the next states are, because they enable 0, what is the next state, simply mentioning the next states over here. But from the equations we computed this state table, and then state transition table also we have assigned a number alphabets A, B, C, D instead of 0, 0, 0, 1, 1, 0, 1, 1, and replace these states with alphabets assigned for A, B, C, D, and so on. The current state output Z is the output which is decided by the current state shown over here. These are the outputs. So from this table we had also obtained the state diagram, which is just the representation of this table over here. Enable is 0, where to move from A, enable is 0, move to C, so this direction, and enable is 1 from A, so move to D, and so on. So this is 1 and 2, and similarly the other cases as well. So now coming to the code of the Moore state machine. So clock enable Z and SREG and SNext, we have declared them as registers, and parameters, because we have these 4 states and 2 flip-flops, and so AB 0, 0, 0, 1, 1, 0, and 1, 1, these are the states ABCD, and then the state memory what we had is SNext, which is assigned to SREG. So from the state transition table, that is one always block which is giving the state memory, and the next state logic which takes enable and SREG and decides this next state is C here, or next state is D. Else if else statements C and C and the C, A and B over here, and D, C and C here, default S next equal to A. So N case and N. So this is another always block for the next state logic. So the coming to the output logic, which is always at SREG. You can notice the difference here. The enable is not to be in the sensitivity list. Case SREG ACD, this is 1, 1, 2, 3, and B it is 0. Okay, so default is 0 and N case. So this is the third always block which we had used. So this explicit state machines not only one edge sensitive behavior, and the remaining two are the combinational logic circuits, right? Output logic and the next state logic. From this we obtain the RTL schematic, which is the clock showing this state memory, and the output of this is SREG, that is the current state, and the current state is taken to decide the output logic, which is Z over here, and this is kept 1 and this is 1 is 0. So there are for other cases according to the logic if else statements used in the output logic. So whereas this is these two muxes are deciding the next state logic with the if else statement. Enable is as an input to this mux, as well as an input to the another mux. Here is a select, it is a select, and here is an input, and the SREG is taken to the as a select line to the decide this next state logic as well, and the enable also here, because we have given enable under the SREG in the next always block, so to decide this S next. So 3 of them after synthesis looks this way, and you can see the feedback also in S next is assigned to D to proceed further for the to compute the SREG. So this is for the Moore machine, so there is no direct input is given to the output logic, that is enable is not connecting it directly to the output logic. So this is a Moore state machine which we had developed then using the module, Verilog module, and then that is synthesized. This is the RTL design. After the technology schematic, if we look at the technology schematic, the corresponding blocks have been realized here. You can see this SREG which is having the flip-flop for the first bit, and there is another flip-flop for the second bit. 0 is 2 bits of current state and for the next state. Okay, so these are the clock is connecting both. It's identifying the edge sensitive behavior, and then we have the LUTs, that is 1, 2, and then 3 and 4 and 5. There are 5 LUTs, and this 5 this is for deciding the output logic. So which has the outputs from here, that is 1 and this one. So to the current state of the flip-flops is given to the output logic, whereas the next state logic has to be the next state logic, it's given to here 1 bit, and it also goes to the this D, this D here, getting it from one is from I0 and another one is I1. So deciding here, I can see we're getting into D flip-flop. So the feedback mechanism. Also the current state, which is over here 1 bit, and then this is from another one which is also linked with the first state, deciding the current state. So the LUTs always try to minimize optimize the functionality of the code. So we have either 2 input or the 4 input, that depends, that is decided by the synthesizer here. So 3 of the blocks can be seen along with the edge sensitive behaviors for the flip-flops for the states moving from one to another. This is for the Moore state machine. The LUTs, again we have all Z is this is for output, and the next state logic, and then next state logic. These two are the next state logic, and the FSM, so which also the flip-flop input is also used using the LUT in this case. So this is the optimized output for that truth table of the LUT, and each LUT is given a truth table, that is, and this is for SREG, that LUT which is using the code. So the most state machine example of this synthesis process, the first step in the real-time implementation as is the synthesis. So these are the outcomes of the synthesis, and after this it would undergo certain steps before getting dumped into the FPGAs. So the third example which I would like to give here is that sequence detector. So the sequence detector, so we had, if you recall that this sequence detector, again the Verilog module is already developed. So it detects 0 1 0 1. So it has 4 states. It depends on the number of bits to be detected, and this is the overlapping sequence detector. So this case we have coded. So here I think if you are in the right track of the track of receiving the bits 0 1 0 1, move to one state to another. Otherwise, if you are not receiving the bit which is expected on a particular state, break the sequence, either stay over here or find out whether the state would form a lead that state to the another state where it can be starting of this sequence or overlapping sequence. So that breaking sequence needs to be decided. Otherwise, if the bits are received in order as expected, you can keep moving from one to another. The final bit is received, then give the output as 1. So the module, Verilog module, we have this, the developed module input, clock, reset, and sequence output. We say here as the whether the sequence is found or not, and the current state also has been taken out as an output. So SREG and the found, deciding because we have these 4 states. These 4 states are depending on the number of bits to be identified here. So all this has a reset also. Always the rate of reset, passage of the clock, reset default state, or define the state which needs to be the reset 1, that is 0 0. Else if the clock is 1, go from one to another. That this is the state memory, and so it identifies the passage of the clock, that its sensitive behavior. And the second always block is the next state logic, SREG or S sequence. So case SREG, where if sequence is 1, deciding the, here I have not drawn the state table because directly you have the diagram. So from this also we can give this. If sequence is 1, next state is A1. If the sequence is 1, next state is A, else move to B. So this is from this 2 of them. Similarly for B, if it is 1, if B at B it is 0, then stay over there. If it is 1, move to next state. So either this can be 0 1 or 1 0 can also be written in any order. So if it is 0 again in C, this is go to D, else go to A. So the next state D, if this is 1, go to C, else go to B. Okay, so this is a overlap sequence. This can be a starting point of the overlapping 0 1, so on. So from this default case and then end. So that's the second always statement completed, and the third one is this for the Mealy state machine. So Mealy state machine, as soon as the sequence is received, the output can be decided with the current state. So always at the rate SREG or sequence, then D, this is the point where we detect the sequence completed the state. So SREG, the current state is D and the sequence is 1, go to, that is going to be found. Else in all other states wherever that it's going to be 0, other combinations and end module. So this is, let's see this, how this particular 3 always blocks getting realized or synthesis. RT is a schematic in which we have the so the change of reset. Reset is given to the flip flops, the state memory, whose output is current state, and the clock, which is given to this as well. So the clock is not associated with other things. And the mux structure is shown over here, where the found output logic, if this is 1, then the combinational logic and them, here is the AND sequence. This is also deciding the output logic. So found is output logic, which is combinational, and this is not registered. We can see over here, if you want to bring it to the the registered combinational logic, then it should be under the passage of the clock here, that should be separately written for that. The next state logic again, then 1, 2, 3. So this is the next state logic output. It's going to the flip flop to decide the switch, and this next state logic actually coming the mux output. So here D is going as a select line to the deciding, that is SREG going to the next state logic, select lines, also going to the output logic. Okay. So these are deciding the next state combinational circuit, which is given over the mux, having the clear mutually exclusive conditions for all of them. So the technology schematic gives the sequence to, this is SREG 0 and the SREG 1. So these are the 2 flip flops over here, then synthesized, and LUT is used for this SREG, that is for the minimization of the logic, and the LUT3, and this is for output logic and whether the sequence is found or not. So in that we have the current state, also the flip flop outputs, and you can see the enable or the sequence which is connected over here in the merely state machine. So the technology schematic identifies those sequence and the clock, everything, and the clock enable is not given, it is assigned to 1 all the time. Okay, that means all the data during this clock pulses would pass in. This is the output, and the SREG, we have got it for each bit. This is 1 and this is 0 bit from here, and the SREG is also fed back to the here in this D to decide on, here you can see, as well as to this lookup table. So there are 2 lookup tables which is used in the flip flops, that is next state logic. These are the next state logic, deciding the next state logic. These LUTs are corresponding to the next state logic. So the corresponding LUT realizations are given, that is 1 input, this is for the first SREG, and second 1 input LUT and the 3 input LUTs, and the 1 is for the output 3 input LUT again, so which gives only 1 for this, and other outputs are 0. For when this is, when the I0, I1, I2 of the lookup table is 1, then it gives 1. So this is giving the sequence detector. So this explicit state machines which we had looked into, the synthesis process of them can be seen that how the flip flop is realized by edge sensitive behavior, which is mentioned in the module. In case of counters and shift registers, that would even if we have the, unless until we have the synchronous counters which is having the same clock, and if you can also model that as a mode state machine, then again that would become an explicit state machine which makes the transitions instead of storage. In the implicit state machines, like the ripple ones, ripple counter, it would make the state transitions from one to another. That is not explicit, and just having the storage operations using the flip flops. 2, 3, 4 flip flops depends on the number of bits. This synthesis process, we have done it for the combinational as well as sequential logic circuits. For the combinational behavior, only all combinational circuits is realizable, for loop will be eliminated in the synthesis process, and if the level sensitive behavior can be synthesized into combinational circuit unless and until there is a mutually exclusive conditions are specified. If not, it will infer a latch. So there are intentional latches and accidental latches. We had seen how those things are realized. So we have to develop the Verilog module which is latch free. In the combinational circuit, there should not be any feedback. In sequential circuit, yes, the feedback is allowed. We have seen in the many cases that feedback is allowed, but in the combinational circuit, we should not have the feedback. So the combinational, which has three different the structural primitives also was realizable, continuous sign statement is synthesizable, and the level sensitive without feedback is synthesizable. And when we write the code for if else structure, it should not miss else structure, else case, and when we use the case structure, we should not miss the default case. So if these problems are taken care in the coding, then synthesis process is not a big problem. So it would easily, the Verilog code module what you have developed will be synthesized into combinational or sequential logic circuits. So we'll see the different cases of arithmetics and arithmetic operations and what is the basics needed for the DSP algorithm implementation from the coming lectures. Thank you.